Hello, SP6GK here. So in this tutorial, I will primarily show you how to perform the electromagnetic simulation of the filter that we have set up in previous video, but also I would like to show you some basic tuning because I forgot to do that in a previous video. So as I said, this will be a little bit shorter to tune this filter because we have this scaling parameter. So if we know that the frequency of this filter will be determined by primarily this radius of the radii of the stubs. Then we can scale this radius by some scale. So I will put this time scale, I think if the, yes, with the capital letter scale. I will copy just this so it will be a little bit faster. Now let's do this the same to the other stubs. Okay. I'm not sure why I didn't see the cursor here. It's not blinking, but should be okay. Now, I will put this closer here with the zoom, and you select the tuning tool. Select the tuning tool. Great, it highlights as a blue. So now I want to open this tune tool here, and you can see that we have some of the elements from our closed for lumped element simulation that we obtained from the tuner. Now, if we go to that schematic so that it doesn't cause any issue or doesn't degrade our focus, I can go to this schematic, select the screwdriver tool, and press on the blue elements to deselect them. So I will deselect the things that I don't want. I close this old schematic and I have only my scale. So now you can see that, for example, I will switch this, for example, value to 1.2. And if you go to the here, this actually will change, right? So the size, the radii of the radial stubs is changing. So let's go to the default. Now, one thing that we have to pay attention when we start the EM simulation is that actually the EM simulation cares about the position of these components. So if I were to change, for example, the length of these components, these traces here, and they would disconnect this radial stub, my schematic would not be correct. Then I would have to press Ctrl A to select all, snap them all, and generate the simulation again. But because the closed form doesn't care about this representation, it cares only about the values on the schematics, we are good to go. So this is the view of our plot from the previous video, and if I move this, you can see I can tune the filter. So for example, maybe I don't want this short response because this might be something wide front end for a receiver, and I want to have better return loss here at 800 megahertz. So let's put a marker here, why not, so that we can see this data. You can see that the auto scaling of the axis is also working. This can be turned off in the project of the graphs that I've shown you before, and you can see that these points are moving. The automatic point is also detecting the changes. So yeah, I guess this is an improvement, right? If you want to have something flat. And you can see that the cutoff is also changing. So if you are not happy with this, of course you can please press a restore button and it's back to the previous settings. I'm happy with this because I might want to use this filter actually for my 1.2 gigahertz some equipment for the amateur radio band, for example. This would be quite decent, I think. But to verify this, we of course want to the star of this video, the EM simulation, to work. So how will we do that? It's actually surprisingly simple, but maybe not very intuitive, believe me. Let's press the right button of your mouse and press duplicate on this closed form circuit from the previous video and rename it this one to the EM, standing of course for electromagnetic. I will make this a little bit bigger, and we have almost everything set up. Here is create stackup. Great. So this is for the AXIEM simulator. The AXIEM is actually quite good balance between precision of the speed of your simulation, and depending of your computer this might take some time. So I will set up my grid at the beginning to, for example, 0.5 millimeters. So this is a little bit larger grid. If you are on the desktop, you can probably go with 0.5 immediately. So let's put 0.5. I usually stop at 0.1. If I want to go really precise, I will put 0.05. This is of course in millimeters, so this is okay for me. And first thing, if you press this one click on this stack up on the extract tool, nothing seems to change. Now this is not correct. So press shift and select every component. Now with the complex structure, this might take some time. I didn't discover anything better, but you want to press right click and go to the properties. This will open the properties for every microstrip component in your schematic. Go to models, and in the EM extraction option, select enable. Press OK and press once again on the extract. Now you can see that these are highlighted, so this will be used in the electromagnetic simulation after we extract the simulation for the schematic. Now go to this stackup. Now this is, I'm not sure why it's not never set up correctly, but you have to do some manual work here. So this is actually set up correctly, but the metal, for example, we don't want this metal. We want to add copper. So please add copper here. Great. Uh, Here is correct. So what we are basically doing, going to the further tabs, is we adding another layers to the AXIEM simulation. Because the AXIEM, you can think about it as a 2.5D simulator. When your layout is divided into mesh, a grid with the X and Y axis, which is what we did here. And then you can also set up it in the Z axis. So basically your dielectric layers, starting with a ground plate dielectric, so your signal conductor, and then some air above. In more advanced options, you can also add, so for example, a metal cover about your circuit, because at higher frequencies, if you add some metal about above your circuit, depending on the height, it will also affect your tuning. That's why you might want to put some absorbers and so on to avoid the reflection from those covers. But we will assume that our PCB is just laying on our bench. We don't put hands close to it, and everything is free air. So 250 from the air is default, and this is okay. This is our substrate FR4, 0.6 millimeters. So this is our very thin substrate that sometimes you can buy for a handmade PCBs. I recommend it if you are into RF. Now conductor thickness, this is correct. Now metal, this I will change to copper because we want to use the copper with its conductivity. Now go to the EM layer mapping. So here you can see that the copper is set to the MT. So this is correct. If I press out this, you can see this is our signal conductor. Great. Right, so this is on the layer 2. We'll check this. We don't use vias. It should be, everything else should be okay. Now go to the line type and also select the metal instead of perfect conductor. This should be fine. You can sometimes change the symbols if you are importing like the S parameters for your symbol for your parts and so on. So this is quite handy, but we'll not use it today. Press OK. Now, important step before going into the further simulation is going to the layout. And we can see that the layout is okay. I will snap it just in case. And now we should go to the extraction right here and add extraction. This created this second layout that is actually the EM layout, and you can see it's snapped together nicely. It has marked ports. There's some more stuff going into this port, but it's all fine now. Let's press this show to the mesh. This is quite important to check before the simulation if it's you know, covered properly. And you can see that it tries to divide this wide length of a 50 ohm trace into smaller rectangles, and also it tries to divide these radial stubs using different triangles, so this is okay. But it complains that the length, the minimum length and the aspect ratio is not correctly. So in this case, maybe it's actually better to spend more time simulating this and going once again to the mesh. And you have seen this large mesh. So let's go to the 0.1 millimeter mesh. Okay, and press again add extraction because we need to update this document. Okay, we don't see the mesh. Let's press again. This might take some time because it's actually dividing this into this grid. And okay, great, no warning. So you should check before whether it can divide this or not. You can see there's some optimization in mind in these effects. Here the mesh is quite thin. Here maybe not so much, but each of these points will be calculated using the method of moments for differential equations, and the mathematics from now will take over and give us some handy results, hopefully, of course. So let's add another graph. This is something that we've done before, so let's call this LPF 1500 EM, wrong button, and this will be also the rectangular plot. Maybe I will not set up every option immediately, but let's here select the EM extract doc. I guess you can also go for the EM, but I will always choose the EM extract doc. The horizontal axis is okay. Let's add as parameter first this S11. It's okay, this color. Let's add now 2 ports second. This should be our insertion loss. Okay, and now the moment of truth, we press the analyze button, and you will see that this takes much longer time. As I said, it's using the AXIEM simulator, which is good compromise between the accuracy and the simulation time. And you know, if you are doing for this for the first time, it might look like a very long process, but actually for the powerful uses that this tool has, I think it's very reasonable time actually. And if you have a lot of time, you can actually play with the odel simulator like Celsius, for example, which might be more accurate, but will take you a very long time. You can see actually it used very short, only 24 seconds, so that's great. I'm doing this on a laptop, my notebook, because Microwave Office unfortunately doesn't work on Linux. Okay, so we are on this EM plot, and let's check the insertion. Before it was about 1.5 dB here. Yeah, quite similar. Okay, this is quite low frequency for the FR4 substrate, so I don't expect that much losses. Minus 28 dB here, so this is actually quite nice insertion loss. Let's maybe do as an exercise again, setting up this measurement to the right side quickly. So this is on the right side, and now put the labels on the left. This is S21, of course, in dB. All right, and I guess left. Now it's right, and this is S11 in dB as well. If only I could put the brackets in the correct order. Right. Okay, let's make it look the same as the previous one with the different width of this trace, and this really makes it stand out, and I think this looks nice. Okay, so we can push this window here and find this window, and you can see, you can compare this like here we did have, actually this has a little bit better, but I think more narrow return loss, but maybe create a third graph, right? Let's see how they both will compare, and we'll name this comparison. It's difficult to talk and right at the same time for me. So let's add measurements. Now we'll want to use different sources, and maybe let's compare only the insertion loss. Let's say that's our main priority here. So from the EM extract and also from the closed form, let's add. Okay, so what we can see from this plot, right? We've compared to uh, the EM extraction. So this is actually our EM extraction, the blue one, and the pink one, or whatever the color this is our closed form. So something that I've mentioned to you in the previous video is that this closed form simulation, it doesn't take into account, for example, the coupling on the physical PCB between these two radial stubs and these traces, right? And this effect would occur at the higher frequencies. And this is exactly what we see here. So here the insertion loss is actually great, really nice, below minus 100 dB. If you have a spectrum analyzer that has this dynamic range, that would be really great. Some of course do, but maybe not all the home equipment. But this is minus 60 dB. This is very typical of a filter, even in MMIC case, of a tight case, and so on. This is quite standard result that I can completely believe in. And you can see actually the stop band here is a little bit better, so this is quite interesting result. But here the filter is of course worse. So I think this is a very nice comparison. You can also use the zoom in area. So this zoom in here. Actually, I wanted to use the view area to see what happens in the passband, and you can see that the EM simulation degraded a little bit faster. So maybe if you want to push this further on, let's go once again to the EM simulation here. Was it? Yes, it's here. And we have the scale. So we have the scale that is the same variable for the both filters, and we want to push this a little bit further on. So here we have the scale for the EM. Let's change this maybe to like 0.8. You can of course step with a smaller step. I will go with something larger just so that it doesn't take that much time and it will show my point. Add extraction. It will overwrite the previous extraction. Let's go to this extraction document. Okay, looks good. Let's turn on the mesh. Will take some time to show us this mesh. Looks good, no warnings. Let's go to the EM simulation comparison. Where was the comparison plot? Here it is, the first one. Okay, and you can see that the blue line, the data for this point was changed. So it's a dark or shaded blue, let's say. So if I press analyze again, it will start the simulation. And it actually knows that this didn't change, so we are only repeating this EM step. Let's give it some time. Perfect. So our goal was really not to create a new filter or retune it by very small step, but to show you how to even perform this tuning. So we were able to manage to push this much further. If you want to put it here, maybe instead of putting 0.8, you would want to start with 0.95. But I hope that now you have some insight into how this tuning works and how the EM simulation can be set up. In the future videos, I would like to show you how to create a schematics and how to capture the schematic of a more complex structure. So for example, things like the EM hybrids, the Wilkinson dividers, and so on. I will also show you the simulation of a 4-layer board so that you can, for example, calculate the 50 ohm traces at the 4-layer board, and there will be some physical experiments with a microstrip structures on a 4-layer boards. This is quite interesting because the thickness of a trace, or the width of the trace, I guess I would say, is very small. So there's a way to overcome that, but that will be in the future video. Anyway, thanks very much for watching. Stay tuned.